Hi again everyone, Tisdell here. In this presentation I'm going to continue my series of videos on partial differential equations. Now the subject of this video is a new technique known as a similarity solution method for PDEs, for partial differential equations. Now I'm going to outline the method and I'm going to discuss a reasonably involved example. Okay, so before I get to that though, where are we going? Like I said, the new method is called the similarity solution approach. And if you've studied a little bit of partial differential equations, you might be familiar with the separation of variables method for solving PDEs, which is a very famous method where you actually separate the independent variables of the solution. Now, in contrast with the separation of variables method, the similarity solution method actually does kind of the reverse. You connect or combine the independent variables in a special way rather than splitting them up. Okay? Now, the method that we're going to see today is very powerful, mainly because it can solve both linear and nonlinear PDEs. Now, in a nutshell, and I'll talk about more about this later, the basic idea is to determine a set of invariant stretching transformations or dilations that leaves the original PDE in question unchanged. Now, continuing that process, what you can do is reduce the PDE down to an ODE, which hopefully is pretty easy to solve. Okay, so I'm going to work my way through the following problem, and I'll talk about the steps as we go. So you can see this is a wave equation or a diffusion equation where k is a positive constant. We've got some extra conditions here. Now U might represent the temperature in a semi-infinite bar at position x and time t. And this condition when x equals 0 at the one end or the end of the bar is known as a flux condition. So we've got a derivative and n is just some known constant. Okay. You can see also here that when t equals 0, the initial temperature, say in the bar, is 0, and the temperature approaches 0 as we move towards positive infinity along the x-axis. Okay, so first step, and here is the sort of table or dot point plan that I promised before, is to determine a set of stretching transformations, x bar, t bar, and u bar, under which the PDE is unchanged or invariant. Okay, what does that mean? Well, suppose u is a solution to the PDE. What you want to do is find relationships between alpha, beta, and gamma, here a is a constant, such that u bar of x bar, comma, t bar is also a solution to this problem. Okay, that's the first step. So let's concentrate on that. Now, usually when I solve problems in my videos, I have blank spaces and I write out the solution. For this one, I've actually prepared the solution and I'm going to annotate to it. The reason is that it's quite long, but the advantage is that you can take this method and this example as like an exemplar solution, which you can take all the steps and all the reasonings and transfer them to solve a whole range of other problems. Now in other videos I'll do simpler problems where I do actually write out all the solution by hand. Okay, so step one. Let's consider these transformations, and what we want to do is we assume that u of x comma t solves that. What is the relationship between alpha, beta, and gamma, whereby u bar of x bar comma t bar also solves that? Okay, so to do this we're going to have to calculate u sub t bar and u sub x bar x bar. All right, so okay, let's consider this derivative first. So if I go up here and I differentiate both sides with respect to t bar, okay, that's a constant, so that's not going to play a big role. All it is differentiating u with respect to t bar. Now, how do I do that? Well, I can, for example, use the chain rule just by sort of rearranging these as follows. Okay, so this way I can write u in the following way. Well, u depends on x and t, and in this setup, x depends on x bar and t depends on t bar. So if I wanted to calculate u sub t bar, I would go down this path connecting to a t bar. And when I move from letter to letter by the chain rule, I form a derivative. So u sub t times t sub t bar. Okay, that's what's here. Okay. And what is t sub t bar? Well, I can work it out from here. It's a to the negative beta. So that's where this comes from. Okay, to get u sub x bar, just go down the left-hand column. When you go from letter to letter, form a derivative. Okay, that's here. Then to get the second derivative, imagine now this is u sub x. So and just run it again. So using the chain rule, we've calculated this derivative and this second order derivative in terms of u sub t and u sub xx respectively. Okay, so now let's see if this and this can be plugged in here and the equation balances. We're going to have to formulate some conditions on alpha, beta, and possibly gamma. Okay, let's start with this. If we just, this is this and this is this. And what you want to do, in order for this to add up to 0, you want to factor out the a's, okay, and then use the fact that u of t comma x, or u of x comma t solves this problem, okay, which means that the difference is 0. So what we would do is we would let this power equal this power. Okay, now if you look at that, you can say, okay, the gammas are going to cancel out, so I don't know what gamma is, but I have a relationship between beta and alpha. Okay, so we've got a little bit of information there. Gamma's arbitrary, and beta equals 2 alpha. So what this means is that for every gamma, and when beta equals 2 alpha, if u of x comma t solves our diffusion equation, then so does this. Okay, this is just u bar x bar comma t bar. Okay, step 2. Determine S and R such that these things hold. Okay, what we'll do, once we've determined S and R such that these things hold, we will actually come up with a form of solution. Okay, so that's like the precursor to this. Okay. Now, if we start with this product, and remembering that beta equals 2 alpha, and remember this is x bar and this is t bar, I replace x bar with what's on the previous page and t bar with what's on the previous page, we get the following. And remembering that, from up here, beta equals 2 alpha, and I can sort of combine everything together, and this will be equal to x times t to the s when this power is 0. So how can I choose s such that this power will be 0? Well, if s equals negative 1/2, then that's just going to disappear. And I now have a value for s. So what does this mean? It means that the new variable will be x times t to the s with s equals 1/2. So in other words, x times t to the minus 1/2. Okay, so let's run through a very similar argument for this situation to determine an R, such that this is true. Okay, well, very similar again, remembering that from previous page, beta equals 2 alpha. You can run through this and you want this power to be 0. So how can I choose R so this is true? Well, you can let R equal negative gamma on 2 alpha. Now, we don't know what gamma is, we don't know what alpha is, but at the moment, that's not going to be a huge problem because we'll be able to determine these things from the boundary conditions. Okay? So now we can move on to step 3 by forming this. Okay, we're sort of P is our new combined variable. Okay, what we hope to do is form an appropriate ODE involving G and P and some boundary conditions. All right. So, this is our form of solution with R equals this and with S equals negative 1/2. That's as far as we can go at the moment. But, like I said, we can determine gamma and alpha, or essentially actually just this ratio really, from the boundary conditions. So what are our boundary conditions? Well, if you look back to the original problem, we've got this limiting condition here, and for example, this flux condition. So how do they translate to this new form? Okay, well, if we take this form and differentiate it with respect to x and plug in x equals 0, just say by using the chain rule, we'll get the following. Now we know from the original problem that this is just a constant. This is a constant, but this term is not a constant. It's got a t in it. So the only way that this can be sort of consistent is if this power is 0. Okay, so what does that tell you about the ratio gamma on 2 alpha? Well, it must be equal to 1/2. Okay, so I can replace this with a half. So I'm feeling pretty good now because I now have the form of solution that we are trying to determine. So we've determined this. What we want to do now is form an appropriate ordinary differential equation involving G and some boundary conditions. Okay, so let's try to form some boundary conditions. Now, if you look carefully at what I've written here, this, because we know that this just simplifies down to 1, I've got a boundary condition already sort of built in here. It's this. Okay, so that's one boundary condition. What's the other boundary condition? Well, let's look at the limiting condition that we had up here. If we look at this condition as x goes to infinity in this form, what happens? Well, as x goes to infinity, it leads us to g of p going to 0 as p goes to infinity. So we have this condition, and now all we need to do is form an ordinary differential equation in G to complete our working, which we'll hopefully solve. So, working from this form of solution, let's calculate u sub t and u sub xx and see what happens to the PDE when we plug these in. Okay, using the product rule and the chain rule, you can differentiate this with respect to t to get the following. And you can differentiate this using the chain rule to produce the following. So let's just combine those in our PDE. So we get the following. Now, you can factor out the 2 to the power negative 1/2, and because t is positive, you can cancel it off. And you get the following. So what do we have here? We have a second order, linear, ordinary differential equation. And from the previous pages, we have this condition and this condition. hopefully this should be enough to solve our problem. Now if you look at this problem, yes, it's linear and it's homogeneous. K is a constant and P is the independent variable of the solution G. So the only thing that makes this look a little bit different from what you might see, say, in a first course in differential equations is the constants, the coefficients are not constant. Okay, the coefficient of G prime is not constant. But this is not a huge problem because we're lucky with this problem. We can notice that for any constant C1, C1P is a solution to this problem. That'll be 0, that'll be C1, C1P, and that'll be C1P. So they'll cancel that and give you 0. So that is one solution to our problem. What we need now is a second linearly independent solution, which we're going to construct by a method known as the reduction of order method. Okay, so that's one solution. We build another solution by multiplying this by an unknown function h and trying to set up a new differential equation for h, which we can hopefully solve, and is reasonably simple. Okay, using the product rule, you can calculate G2 prime, G2 double prime, plug them in here, and form a new differential equation in h. Now if you do that, you'll get the following. Now yes, it's still second order, but really it's only first order. Think of this problem as a first order DE in h dash or h prime. Okay, so you move the 2kp down there and you solve for h prime just by use of an exponential function. Okay, so here it is. C2 is a constant. And if you integrate this, use your log laws and recognize that p is positive here, then you get the following for h prime. So I got h prime. What I'm going to do is integrate it from p off to positive infinity. Okay, now this improper integral is well defined, and this h of infinity, I've just sort of put that in there to save a bit of space, is just the limit as p approaches infinity of h of p. Okay, now and let's just, whatever that value is just going to be the value of m. Now it's well defined, by the way. Now if you integrate in here by parts, then you'll get the following for h. So we're in a strong position now because we have essentially solved, or at least determined, a general solution to my problem 3. Okay, I've got that, where C1's a constant. I've found h of p, so I've got G2. Because this is linear, I just add the two solutions together to get G. Okay, and here it is. Okay, now what is M, what is C1, and what is C2? Well, we can determine them from our boundary conditions. Okay, so let me just see if I can pull them out. Here we go. So here's one boundary condition, here's the other boundary condition. Now let's look at this one first. Okay, so this is just this. Okay, so as p goes to infinity, let's have a look at what happens to g of p. This will go to 0. This product, it turns out, will go to 0. And this will go to 0 only if m plus c1 is 0, because p obviously goes off to positive infinity as p goes to infinity. So we can conclude then that this coefficient must be 0. So that term actually disappears. Okay, and this is our sort of simplified form. Now we haven't used this flux condition yet. So let's take this, let's differentiate with respect to p, plug in p equals 0, and set it equal to n. So you will differentiate this, use the product rule here and the fundamental theorem of calculus, and when you put in the p equals 0, a lot of terms disappear, and you get the following. Now, I can actually compute this improper integral. I can get a definite value for it just through a change of variable, just by simplifying what's up here. If you let, say, z equal the square root of what's up here and calculate the differentials, then this goes to this, and the value of this special improper integral is known. In fact, I think I've proved it in other videos. This is just root pi on 2. So now what you have is you have C2 in terms of n, and n is some constant which you know from the original problem. Okay, so that's 0. That's now in terms of n, and we're almost finished the problem. Okay, so if I just rearrange that last line, I can get C2 in terms of n. So replace this with this, and I've got my g. So we're very, very happy now because we have solved that ODE that we wanted to solve. Okay, and the associated boundary conditions. So we're almost finished the problem now. We've got g, we know g of p, we know that p equals that, and to get u, we just take g, replace p with this, and multiply by t to the power 1/2. Okay, so let's do that. So we kind of, as far as the summary goes, we're at the very last stage now. Let me see if I can find it here. Here we are. We've done that, done that, done that. We've solved it. We've solved it, and essentially we're doing the very final step, which I haven't mentioned, is getting back to u. So this then is our solution. Now, I haven't simplified this as much as I could, because I'm thinking this is already a pretty long presentation. So you can cancel off that and do a bit more cancellations. Okay, so a couple of things. You can take this a little bit further and express, say, this in terms of the so-called complementary error function, which is a special function used in applied mathematics and PDEs. Now, a couple of sort of summary steps to take you through these problems. Determine a set of stretching transformations under which the original PDE is invariant. That means that if u of x comma t solves the PDE, so does u bar of x bar comma t bar. Determine S and R such that these are satisfied. Once you have those, you can get a general form of solution where you combine the independent variables in some way. And what you do then is you form an appropriate ODE and boundary value problems to work on for g in the new independent variable p. You solve it, if possible, and then you relate everything back to u. Okay. Now, a couple of things. In this step here, I claim that as p goes to infinity, this term goes to 0. So if you're wanting something to do independently of this exercise or presentation, show that the limit of this goes to 0 as p goes to infinity. Now, in other videos, I will show you simpler and possibly shorter presentations on how to solve these problems. But the really good thing about taking the time and the effort to type up all these solutions is that the solution method here is like a general guide to map out the solution methods for other problems. Okay, so if you're stuck on applying the method, you can always come back to this video, and as a general rule, you think about these 4 or so steps. So in other videos, I'll do some more similarity solution method type problems. I hope you can join me for those presentations.